Hello guys, so welcome back to our course. This is the fourth lecture. So last time we demonstrated two currents that can flow in a semiconductor, which are the drift current and the diffusion current. And it's now time to to explore our new device that we're gonna use in our analog circuits, which is the diode. Di, from the name, has two things, and it's basically founded on the concept of a B-in junction. And basically, a B-in junction is that you bring two samples, one sample N type, one sample and B type, and just you connect them to each other. You make a contact between them. Of course, in real life, we are not doing that. We are not doing that alone and just make a contact between them. But we do it in another way. But at the end, you will have some N-type region and B-type region of silicon, and both have a contact. Okay, both have a contact, and that will create a diode for you. Okay, so in that part of the course, we're gonna explore the properties of this B-in junction so that we understand how the diode work. Then we use it in a circuits. So we're still in physics right this moment. Okay, to understand how B-in junction work, let's make a simple experiment. Just bring an N-type sample, not a B-in junction, just N-type sample like this. Okay, and connect it to a meter and a variable battery or a variable voltage source. And then we're gonna, just like Ohm's law, we it changes the battery voltage and measures the current that is flowing into the N sample. Okay, and let's now ask the question: what you expect? And basically, here the answer should be that this N-type sample should be just like a resistor. So this should be just like a resistor with some resistance R. Okay, so the relation between I and V for that sample should be something like this. Straight line crossing zero, the axis, the zero axis for V and I, and the slope is just 1 over R, because here I on the vertical axis and V on the horizontal axis. What is R? R actually is the equivalent resistance of that N-type sample. And how to calculate it, if we know the doping and the stuff, this is your homework. So part of your third homework will be to calculate a resistance for N-type sample. Okay, now let's redo this experiment for a B-in junction. As you see here, we have N region of silicon. I mean, a region that has a majority of electrons carriers and a minority of B carriers, or the holes, and another region here which is B type silicon, which has majority of holes and the minority of electrons. Okay, and as if you remember, the symbol for the density of the electrons in the N region is called Nm, and the symbol for the holes in the N region is Bn, and the opposite for the B type, Bb and Nb. And it doesn't have to be equal, I mean equal distributions, I mean no, equal densities. I mean Nn doesn't have to be equal to Bb, and Pn doesn't have to be equal to Np. Okay, just N type and B type, and just to connect them to each other or make a contact between them. So this is the contact or the junction. Okay, and we're gonna connect, a variable battery and measure, it changes this battery and measures the current. And here is the result. We will not see a linear, relation anymore. We're gonna see something like this. Okay, something very similar to this. And we're gonna explore this in the future, but first I want to show you the difference between both. The first difference, it's not linear anymore. the relation between I and V is not linear. So the relation is the first difference, it's non-linear relation. The second prominent difference here is that as you see here for the Ohm's law case, in negative, when you change the voltage in negative, you will still have current, but with negative. I mean, if you reverse the voltage polarity, you will get a current, but this current will also be in opposite direction. But here, no, you are getting, very small current. So this is very small, approximately 0. So this is very small reverse current. It's very small to the extent that you can say that when you flip the polarity, it's open circuit. When you flip the battery, okay, it's open circuit. Okay, guys, so this is basically, a highlight of what we're gonna see as a result of this junctioning two opposite, samples to each other, N type and B type. Okay, so let's continue. Let's now understand how this happens. And the basic, principle for it is how to understand the junction current, I'm sorry, the diffusion current that we took last time. Okay, so we said that if you have non-uniform distribution of carriers, the carriers will move from the high distribution region to the low distribution, low density regions. Okay, either for holes or electrons. So do we have the same, situation here? Yes, we have, because remember we contacted them to each other. So some electron can move from here to here, some hole can move from here to here. There is a contact. Okay, they are connected. So in that region we have excessive electron. So excessive electrons. And here we have excessive holes. So we have here in the B region high density of holes, here low density of holes. We have here high density of electrons, we have here low density of electrons. And that's enough to create diffusion current. So holes will diffuse from that region to that region. And the electrons will diffuse from that region to that region. Okay. And we're gonna get something like this. See, in the beginning, you have constant uniform distribution or density of NN across the whole N-type material, and uniform density of holes across the N-type material. Same for B-type material. But now, no, it's not uniform anymore. So the density here is larger than, for example, the density here. The density here is lower than the density of holes here. So this is due to what? This is due to that some holes from the N side, from the B side goes to the N side. So this distribution of holes in the N side has increased a little bit near the junction, near the contact here, or the junction. Same for the electrons. Electrons move from here to here, from N to B. So that the minority carriers in the B type now increased a little bit near the junction or near the contact. Okay. Now the big question: does that behavior continue forever? I mean, at 1 second we have this, at 2 seconds we have this, at infinity, do we still see motion of holes from B to N and the motion of electrons from N to B? And the answer is no. Basically because if you look here, this is different from this. Because here I have a battery. There is a closed loop circuit. Here I have an open circuit. It's open. Okay. Since it's open, there is no current, right? So there should be some time in the future after making the contact at which the current should be zero. Okay. And that's actually the case. So one thing here that we should note is that whenever a hole leaves the B type into the N type for that direction here, it leaves behind a negative ion, boron, for example. So each hole moves will leave behind negative ion. And again, for the N-type material, for each electron moves from N to B, it will leave behind a positive ion. We have now ions, negative ions, near the junction, and the positive ion near the junction from the N side. And why I'm saying these ions are near the junction or the contact? Basically because near the junction, the holes and the electron near the junction will be the first to move towards the other junction. That's intuitively also. Okay, so most of the ion, you know, all of them actually are created near the junction. So, okay. So why these ions will eventually lead to the you know, to the end of this motion between end of this motion of holes from B to N and electrons from N to B. And this is basically the concept of drift again, you know. Okay, so let's understand it very well. So here we have negative ions, here we have positive ions. Okay, and remember, these ions are not moving, they are not contributing to the current. Okay, so it's like you have a negative electrode on one side and a positive electrode on the other side. Just one, you know, electrode means, you know, one piece of metal with negative and another piece of metal that is positive. Okay, whenever you have a positive and a negative, then you will have an electric field from the positive to the negative. Remember the drift velocity last lecture. Okay. Okay, now let's understand the effect of this electric field, newly created electric field. By the, it was not there because before the contact. Once we make the contact, it will begin to be created and increased by time. Okay, so this electric field. Okay, if we have, for example, negative charge electron in that region of the electric field, so the electric field will create a force on that electron, and this electron will move toward the positive electrode. It's attraction force. If we have some positive charge, which is the hole, it will move toward the negative electrode. Okay, so let's now see where is the original motion of electrons and the holes. So holes originally moves from B to N in that way. So let's draw them with another color in that way. And the electrons originally move from N to B in that way. So basically now we have two currents. We have diffusion current. So we have two currents. We have diffusion current. And we have number two, drift current. and both are opposite to each other, and both in opposite directions. Remember, at time equal to 0, we have diffusion current, and we don't have drift current. But then, when eventually, for each electron hole pair that crosses, the junction or the contact, there will be two ions, negative and positive. Okay, so this will create, the drift or the field, the electric field. And as the movement increases, the electric field will increase. I mean, the opposite current will increase as well. So this will continue until some point in the future in which the drift current will cancel the diffusion current and the motion stops. Okay, so if we, if we have, a time trace, let's say so at time equal to 0, you have the contact just formed. Then at some time later, some holes start to move from here to here, and some electrons start to move from here to here. So we create negative ions on the p side, positive ions on the n side. This will create electric field in that direction, and the drift current in the same direction. At t equal to infinity, I mean, after a long time, then we have such a situation. We have a strong and if electric field that stops, the motion of holes from B to N and the motion of electrons from N to B. Okay. And actually, this is what's called equilibrium condition. Since we have two, phenomena that cancel each other, we call this equilibrium. That's why we are studying now, the B-in junction under equilibrium. So this is the first thing to understand, how the junction works if there is no, electric field connected, or I'm sorry, if there is no battery connected to it, if there is no voltage, if there is no potential across the B-in junction, if it's just open circuit. When it's open circuit, we will have such a situation. We will have strong diffusion current that decrease over time, and we will have created drift current that becomes stronger by time. And at some time in the future, both they will cancel each other. So if we, just sketching how we can imagine, the relation between the drift current and the diffusion current. So if this is the I diffusion by time, if we want to imagine the diffusion, the drift current, it would be something like this. Look, the end here is 0. If this is, for example, let's say it I naught, whatever is equivalent. So this will be I naught as well. That's why they will cancel each other. Okay? So this is the equilibrium condition of the B-in junction. In the future videos, we're gonna continue exploring the properties of the equilibrium condition, then highlight or demonstrate other conditions for the B-in junction, which are basically reverse and forward. Basically, you can think of, okay, this is open circuit, but our circuits usually is not open. We have circuits that, we connect devices to each other. We have closed circuits, and that's what we're gonna take in the future. But we should first understand well the equilibrium conditions. So see you guys.